Okay, let's start chapter 2. We're only doing two sections. 2.1 linear functions, which is an intro to everything about linear. Then 2.2, which you see that I scratched off because I was going to put these together, but it'd be too long of a video. But 2.2 will come after this, graphs of linear functions. Let's get started. So imagine placing a plant in the ground one day and finding that it has doubled its height just a few days later. Well, if it doubles every single few days consistently, that'd be very linear. Although it may seem incredible, this can happen with certain types of bamboo species. These members of the grass family are the forest growing plants in the world, are the fastest growing plants in the world. One species of bamboo has been observed to grow nearly 1.5 inches every hour. In a 24-hour period, this bamboo plant grows about 36 inches, or it's an incredible 3 feet. That's a constant rate of change, such as the growth cycle of this bamboo plant is a linear function. Well, that's the secret. The words that we just read, constant rate, right here. I don't like how that looks. Okay, so that's, try to underline that better again. Let's see. Constant rate of change. By the way, that's slope. Constant slope. That's what the rate of change is. Such as the growth cycle of this bamboo plant, it's a linear function. Linear has a constant slope, not a float, slope. Recall from functions and function notation, that's our lesson 1 in chapter 1, that a function is a relation that assigns to every element in the domain exactly one element in the range. Linear functions are a specific type of function that can be used to model many real-world applications such as plant growth over time. In this chapter, we will explore linear functions, their graphs, and how to relate them to data. Just as with the growth of a bamboo plant, there are many situations that involve constant change over time. And we're going to talk about this train, so I'll get that to the next slide. But here are the objectives for this 2.1. In this section, you will represent a linear function. You will determine whether a linear function is increasing, decreasing, or constant. You will calculate and interpret slope. That's our constant rate of change. You're going to write the point slope form of an equation, and you're going to write and interpret a linear function. So what I was going to finish up is, such as this train called a maglev train. This where to travel. It's used for traveling long distance, and that the train maintains a constant speed of 83 meters per second for a period of time. Once it is 250 meters from the station, how can we analyze this train's distance from the station as a function of time? Yeah, I challenge you to figure out how fast this train is going in miles per hour. 83 meters per second. Think about a 100-meter dash. In 1 second, it's doing what some people do in track and field 83 times. That's pretty awesome. Representing linear functions. That's what we're going to do right now. This function, the function describing the train's motion, is a linear function, which is defined as a function with a constant rate of change that is polynomial degree 1. What does that mean? If I say f of x equals x, it's in your toolkit. It's also called a parent function of a line. There's an exponent of a 1. You just never write it. Even other lines that we've looked at, g of x equals to 3x minus 5. Again, the exponent is a 1. So we say it's a polynomial, because poly means many and nomial means terms. This happens to have one term. This happens to have two terms, but you've seen other polynomials. Has a degree 1. Degree 1 implies that this exponent is a 1. This exponent is a 1, but how often do we write that? We just don't, okay? There are several ways to represent a linear function, including word form, function notation, tabular form, graphical form. We will describe this train's motion as a function using each method. So we're going to explore all those methods real quick. Representing a linear function in word form. And I know you could just read this yourself. I'm not even sure this is worthy to write notes on. So I'm just setting up the chapter of functions, even though we're not going to do the whole chapter. In word form, let's begin by describing the linear function in words. For the train problem we just considered, the following word sentence may be used to describe the function relationship. Now, there are other sentences you could write. There's not one answer, but let's talk about this train. The train's distance from the station is a function of the time during which the train moves at a constant speed, plus its original distance from the station when it began moving at a constant speed. We could say the speed is the rate of change. Recall that a rate of change is a measure of how quickly the dependent variable changes with respect to the independent variable. We've talked about those before, and you had it before. When you have a function, whether it's a line or anything else, and we make a table of x and y's, your teacher always says, pick some good x's. You can pick almost any x, depending on, of course, we've already learned there are some restrictions in some domains from some function, but a line, you can pick any x. Once you pick the x, which, by the way, are independent because you just made them up, decided, the y value gets calculated because you're plugging in the x. I can put a little comment up here like y equals 2x minus 1. And if I say let x equals to be 0, let x equals to 1, well, I independently picked those, and I'm going to plug them in because the first one's going to give me y equals to 2 times 0 minus 1. 2 times 0, I should put that in parentheses, is still 0. Minus 1 is a negative 1. So that negative 1 that we got is depended on the x that I picked. Since I picked a 0, the x is the independent, and the y is depending on that. Now, if I pick x as 1, then the y value changes because it depends on what x I chose. So if I plug in the 1, well, 2 times 1 is 2, and 2 minus 1 is 1. That's going to give you a positive 1. So if I write that out, this is the other y. 2 times 1 minus 1 is 2 minus 1, which is a positive 1. So that's what we're doing there. Okay, where was I reading? All right, I'll read that paragraph again. The speed is the rate of change. Recall that the rate of change is a measure of how quickly the dependent variable changes with the respect to the independent variable. The rate of change for this example is constant, which means that it's the same for each input value all the time. That's my input. Those are my x's. Increases by 1 second. The corresponding distance, which is my output, that'd be like if I did my graph and I'm graphing this thing, I'll back that up and same for each input value of time. So there's my input. Oh, don't mean to erase. Time. And my output value will be my distance. As the train goes through time, it's constant speed because the slope's the same. The d is being dependent on whatever time we're at, because the longer the train goes, the farther distance I am from the station. The corresponding distance output increases by 83 meters. Well, every second. Every second. So the distance changes. Every second, the distance went 83 meters. That's what it means, 83 meters per second. The train began moving at this constant speed at a distance of 250 meters from the station. So it took some time to pick up that speed. So let's be totally honest. We're really not starting at 0. So I will get rid of that picture because it's not accurate. Because 0, when the train took off at time t, 0 stands for how far away from the station. Well, I think I said it was 200 and I'll find it again. Trying to find 250 meters. We start the clock at 250 meters because that's how long it took for that. So there was some seconds in here that train was moving, but it wasn't going at that speed. It probably was a lower speed, and then it probably went up and boom. Once it got there, it went straight, okay? But the train has to pick up, so that's your y-intercept, by the way, at 250, if that was my equation. And we'll look at it again. Now, that was with words. We're talking about it. Representing a linear function in function notation. This is going to take you back to lesson 1. Another approach to representing linear functions is by using function notation. One example of function notation is an equation written in the form known as the slope-intercept form, where x is the input value, m is the rate of change, and b is the initial value of the dependent variable. So usually that's called your y-intercept. It's where if I started at 0, if x was 0, and like the last problem, x was actually 240, so we might see that coming up in a second. But your equation form, y equals mx plus b, function notation is f of x equals mx plus b. Okay. In this example of the train, we might use the notation d of t, in which the total distance, d, is the function of the time t. The rate m is 83 meters per second. That's your slope. And the initial value of the dependent variable b is the original distance from the station, which is 250 meters. That's why I wrote that 250 where the rate of change started. We can generalize we can write a generalized equation to represent the motion of the train. So in actuality, that line that I started didn't really start at 0, 0. It's going to be shifted up because this is my y-intercept. So more correctly, the graph would be up here is my 250. That's my original distance at time t is 0. It's here that the train starts at a constant speed. All right, let's represent a linear function in a table. That's what tabular notation means. And I'm sorry to read all this stuff to you. It's just the introduction of the chapter of linear stuff, so most of it isn't. It's setting it up, that's all. The third method of representing a linear function is through the use of a table. The relationship between the distance from the station and the time is represented in figure 2, and that's just a table there. You see you got time in the, that's like my x values, and then these are my these are my y values. Just like you would x and y's, and so the time changes from 0 seconds to 1 second, 2 seconds, and 3 seconds. So from this table, we can see that the distance changed by 83 meters every second. Get it? So right here, 250 is how far we are from the station once we reach this constant speed, okay? And so we're just saying, I'm going to start my clock right now at time t is 0, even though the train had already moved. It didn't just at 0 seconds shoot like a bullet. No, the train had to move and it took 250 meters of running time to actually hit that speed of 83. I believe it was 83 meters per second. Yes, it was. So it's constant. So 1 second, I add 83 to the 250. 1 more second, I add another 83 now to the 333. Another second, I add another 83 to the 416. It just, you keep adding 83. The distance keeps changing 83 every second. Okay. That's the table. And this might be the last one, representing a linear function in a graphical form. What is that called? A line. A line. Another way to represent linear function is usually using a graph. We can use the function relationship above, d of t equals 83 plus 200, 83t plus 250. That means, 250 was my distance from the station once it reached this constant speed of 83 meters per second. And to draw a graph represented in this figure 3, hopefully we'll get to that, notice that the graph is aligned. When we plot a linear function, the graph is always a line. The rate of change, which is constant, determines the slant or slope of the line. The point at which the input value is 0 is the vertical intercept, or we know it as the y-intercept of this time. We can see from the graph in figure 3, I hope I have that graph coming up, that the y-intercept in the train example we saw is 0, 250. That's the ordered pair. Represents the distance of the train from the station when it began moving at a constant speed, because prior to that it had to speed up. It didn't take long to speed up, apparently. It didn't take long. It didn't. 250 meters is all it took to get squared away. Now, I hope I have the picture coming up, but just in case I don't, remember what it looked like. At time, this is my time axis, this is my D axis, and at time t is 0, I finally was going 250 meters. That's how far I am. And then the train, and I don't know what it did back here. I don't know how many seconds it took. And of course, I'm in the negative time just because it's before. That thing could have sped up, sped up, sped up, and then boom, then all of a sudden shoots out like a bullet now. Boom. That slope is 83 meters per 1 second. Rise over run. And they are units. 83 stood for something, 1 stands for something, but in reality, we would just say the slope or the rate of change was just 83. And we know it means meters per second. Meters per second. We know it means that. Let's see if the textbook drew one. There it is. Maybe that looks better than mine. Of course it looks better than mine. Continuing this, representing our function in graphical form. Another way to represent is visually, using the graph. And that graph is more detailed, of course. We can use the function relationship from the above, d of t equals 83 plus 83t. I keep forgetting the t, I'm sure I am. Plus 250, so forgive me. To draw a graph represented in figure 3. Notice the graph is a line. When we plot a linear function, the graph is always a line. Go figure. The rate of change, which is at a constant, determines the slant or slope of that line. The point at which the input value is 0, that's right here, when the input value is 0, is the vertical intercept, way up here. And you can see where it is. It's at 250. We call it the y-intercept. When we can see from the graph in this figure that the y-intercept in the train example is this point right here, 0, 250. It represents the distance of the train from the station when it began moving at a constant speed. Okay, now enough of that nitty-gritty. There's our definition of a linear function if you truly need it. I hope you don't, but a linear function is a function which graphs a line. Linear functions can be written in slope-intercept form. This should take you way back. F of x equals mx plus b. Where'd my marker go? I don't want it down there. Let me get rid of that. I didn't mean to write that. mx plus b. Slope-intercept. Why is it called slope-intercept? There's your slope next to the variable. B is that vertical intercept or the y-intercept. This is my slope. Okay. What'd I write m for? It's already labeled an m. Slope. B is the initial or starting value of the function, technically we say, because we put it at time t is 0. When input x is 0, or t in that case for the train, and m is the constant rate of change or slope of the function. The y-intercept is always going to be 0, b, 0, b, 0, b. You always look at a line to say, where does it cross this axis? Wherever it crosses is your y-intercept. It's a point. And that's going to be labeled b, and then that's going to be the 0. So 0, b. Always. Which I think you know that already. So example 1. Using a linear function to find the pressure on a diver. So I got this picture here, and the diver is going to go underwater, and that causes A lot of pressure because the weight of the water is on top of the person. So that's why they wear suits. The pressure P in pounds per square inch, called PSI. On the driver is figure 4, that's the picture. Depends upon her depth below the water surface. D is how far down we are in feet. So the farther you go, the more pressure there is. Anybody been a diver, they know that when you go and touch the bottom of a deep, deep pool, you can feel it in your ears. This relationship may be modeled by the equation P of D, which is pressure at a certain distance. Let me get a color here. Pressure at a certain distance is equal to 0.434 D, so that's just a decimal number, plus 14.696. They want us to restate this in words. I believe it said that. Yes. So I'm not going to write it. I'll say it, and then we can see what the author said. As I see it, the pressure on this diver, D stands for feet, so every foot deeper that she goes, I multiply by 0.434. So that's my slope. And what did it say up here about slope? Didn't it say anything about it? It didn't say nothing. But it's going to mean how much pressure per foot. Pressure per foot. So 1 foot gives you almost a half, a 0.5. 2 feet is going to be doubling it. 3 will be tripling it. So every time you go a foot down, you're getting more pressure. Now, this 14.696 is an interesting little character. I guess even before you start going down, you already have pressure. Think about what pressure is on you before you even hit the water. So there is still pounds per square inch hitting us every day coming from above. So you can't get rid of this. You're not going to get rid of that. But as you go farther down, you are adding more pressure to you. I don't know if I did justice. I may have talked too much about it, but let's see. What did the author say? I'll let you take a look at it. Well, actually, I want to kind of read this myself too, just to see. Right here, I'm reading where it says solution. Okay, so let me see what this one. I want that color. To restate the function in words, we need to describe each part of the equation. The measure of a function of depth equals 434 thousandths. What is that? 434 thousandths. That's a decimal. Lost my pen again. 434 thousandths. That means there's a decimal there. Times the depth. So there's my D. 0.434 depth. So my pressure, that's what this is saying, my pressure, but it's in words. And I'm putting it back into the equation because it makes more sense to me in the equation, but I see where that came from. But then we're adding something to it. What are we adding? It says here plus 14 and 626 thousandths. I'll just look at it up here. 14 and 696 thousandths, 0.696. is the pressure PSI. That's the pressure. This amount times every foot plus this amount of pressure. The rate of change is the 0.434. That's my slope right here. This is my y-intercept. Now let's talk about determining whether a linear function is increasing, decreasing, or constant. I really don't think I need to spend any time on this. We've already been going over this in all the other functions. Because this function is positive slope. Even if it was a curve going up, we say it's increasing. It just means that any point you pick from this point, that's my first x, to another x, the y value got higher. Another x, x3, the y value got higher. It never did decrease. It never went down. It's going up, so it's always increasing. Lines always constantly increase, constantly decrease, like in this case, because if I take an x1 here versus the one next to it over here, it went down. The y value went down. The y value went down. Here, the y values go up. This is my constant function. The y values never change. No matter if I pick an x out here or I pick an x out here. So think of it like this. Positive slope, negative slope, zero slope. Slope, slope, slope. And is there a reason I have this slide again? I don't know why. Now, this is just a rule. This is just a rule that increasing and decreasing and constant, I don't know why they didn't write constant because here's increasing, here's decreasing, and here is constant, if the slope is greater than 0. Increasing, duh, positive. If the slope is less than 0, that's negative. If the slope is equal to 0, that's what I said earlier on the other page. It's constant. Not a biggie. Example 2. Deciding whether a function is increasing, decreasing, or constant. Oh, okay, maybe I missed something in that last problem. I'll take a look at it. Okay, what they're doing on this example. Deciding whether a function is increasing, decreasing, or constant based on some scenarios. Studies from the early 2010s. That kind of sounds funny, 2010s. Indicated that teens sent around 60 texts a day when more recent data indicates much higher messaging rates among all users, particularly considering the various apps that which people can communicate. So you don't just talk with your text messages. You message in Snapchat, you message in Facebook. So there's a lot more going on than just text messaging on your phone. For each of the following scenarios, find the linear function determines the relation between the input value and the output value. Then determine whether the growth of that function is increasing, decreasing, or constant. So this is technically your question. So I would want you to take a few minutes to look at those. You could have paused the video, I suppose, instead of me waiting. So remember, the study shows that 60 texts a day, even though we think there's probably more because of other apps. But anyway, let's stick with 60. A, the total number of texts a teen sends is considered a function of time and days. The input is the number of days, and the output is the total number of texts sent. So there's nothing talking about any extra cost. It's you get 60 per day. So your function would just be 60 per day. And I don't know what variable they're using. It doesn't matter. I'm going to use probably f of x. We'll see. So I'm thinking A would be just f of x is 60 per day. Now, tell me about that one. There's no y-intercept other than 0. So your slope is 60. So I think that's increasing. Let's look at B. B says, a person has a limit of 50 texts per month. Or no, sorry, 500. 50 would kill us. 500, this was the old days. 500 texts per month in their data plan. The input is the number of days, and output is the total number of text messages remaining for the month. Here's your key word, remaining. You only get 500. So this time, f of x, you only get 500. But every day you're using 60, minus 60 per day. So check out the slope. Minus 60 is your slope. That's your slope. That's decreasing. Well, of course it's decreasing. As the month goes on, you're getting less text messages are going to be available for you. Here, you're just using 60 per day. Every day, 60, 60, 60, 60. It doesn't look like you're limited. Just you do 10 days, you can make 600. I think. We'll check what the author says. The third one says, a person has an, well, that one's the unlimited. So I suppose A was not unlimited. Maybe I'm going to rethink my answer. I'm going to read A again. The total number of texts that teens sends is a function of time in days. The input is the number of days, and the output is the total number of texts sent. I'm going to stick with that answer unless I have to eat crow. So C says, a person has an unlimited number of texts in their data plan for a cost of $50 a month. It says here that the input is the number of days. This time the output is the cost. That's my output. So I'm still going to call it f of x, even though it stands for the cost. No matter how many texts I make, my cost is $50. Doesn't matter how many text messages. That would be constant. Okay? Let's chew on that. We're supposed to talk about the words. I didn't write the words. I just talked it out. Let's see what the author says. Other than using a different variable than they probably told me to use. I used D. I see they used X. 60X for the first one. And yes, it was increasing. Whoop, wrong pen. Not that you probably saw it. Increasing, so yep. The second one starts with 500, take away 60 every day. And I said that was decreasing, and it says that there. They do a lot more words than I was going to. And then here you just played a fat $50. So it's flat, so yeah, it's going to be constant. So I feel okay with it. Calculating interpreting slope. Rise over run. Rise divided by run. Change of y's over the change of x's. Change of y's means to take one of the y's and subtract the other y. But it doesn't matter which one you go first. It's the same answer if you switched it around. I mean, normally we say y2 minus y1. It just means one of the y's minus the other y. You could take the other point and switch them around, y1 minus y2, as long as your x's is also coming from that same ordered pair, x1 minus x2. That's how you calculate it, but you need 2 points. Notice the fancy definition. It's the functional value of x2 minus the functional value of x1 divided by x2 minus x1. Because that means one of the y's, one of the y's. That's what those mean. They're just y values. And this is just in your textbook. It's the same thing I just got done going over. But they added a picture of a line. It's a generic picture. Just, don't want to write on it. At least not yet. Picture of a line. Doesn't matter. They could have drawn it anywhere. And you grab 2 points. I grab this point. I grab this point. Doesn't matter. Just realize that the distance here, look at the distance here. The distance there, vertical distance, is the difference of your y values. Doesn't matter if you take the y2 minus y1, or you take the y1 minus the y2. It doesn't matter if you go this way or that way. And the distance between the x values is your change of x's. I think it's pretty understood. You probably already got that. And I'll just let it come back in case you were writing anything down. There's that formula again, calculating slope. There's your directions how to calculate slope. If you need it, write it. Keep doing extra pages. Now this is your example 3, finding the slope of a function. Notice they just gave us 2 points. They just gave us 2 points. And if I was to want to waste some time and put a picture, I'll do it for you. 3, negative 2. 1, 2, 3, 1, 2. There's that point. The other one was 8, 1. Once you know it's too big. So I go 3, 4, 5, 6, 7, 8, 1 up. So we're calculating the slope of this line here. Okay? I can tell right now it's positive. So should you. So it just doesn't matter. Your slope. Grab one of the y values. It doesn't matter. Okay, I don't know what you said. I think I heard somebody say 1. Okay, 1. There, I just grabbed it. 1 minus what? A 2. No, you're wrong. What do you mean I'm wrong? That's not a 2. That's a negative 2. Be very careful. Now we come back and we grab the x's. Let's see if they trick us. Since I grabbed the 1 first, I have to grab the 8. 8 minus what? 3. Yeah, this time you're right. It's a 3. Just be careful here. Famous last words is, I won't mess that up. These 2 go together to make a plus. 1 plus 2, all divided by 5. 3/5. That means, let's interpret that. From here, rise over run. 1, 2, 3. 1, 2, 3, 4, 5. That's something? I went 1, 2, 3. Up. 1, 2, 3, 4, 5. Across. Rise over run. So I feel confident with my answer. Let's take a look at the authors. Yep, it's there. What they do an analysis. This is what I already mentioned. As mentioned earlier, the order which we write the points does not matter when you compute the slope of the line, as long as the first output value or y-coordinate used corresponds with the first input value, the x-coordinate. And I think I have it right? I didn't look at it close. 3, 5. Yep, that's what I had. Now you try one. This is for you. You should pause it and work it out yourself. Let's see. If f of x is linear, and we have two good points, 2, 3, and 0, 4, they're points on the same line, find the slope. Real quick, find the slope. I'm gonna reverse my thought. I'm gonna take the 3 first now. Always go for the y. 3 minus the 4 over, since I started 3, come back to the 2. 2 minus the 0. 3 minus 4 is a negative 1. 2 minus 0 is still a 2. That's a negative half. And I bet you if I'd have plotted those points, it would have looked definitely a negative slope. Let me just do it. 2, 3, and 0, 4. 1, 2, 1, 2, 3. 0, 4. 0, 1, 2, 3, 4. Sure enough, look at that. It's almost magic. Almost. Finding the, example 4, finding the population change from a linear function. Looks like population city increased. They had 23,400 people. Now they have, the next year they look at was 27,800. The years were 2008 and 2012. So I'm going to make those ordered pairs. The population increased, so that would have been, I'm looking at the year, comma, pop. That's my ordered pairs. So 2008, 2008, we had 23,400. Then in the year 2012, we had 27,800. I don't think it's going to be any different than what we just did. Just the numbers are uglier. Slope. I'm going to grab I like to usually grab the bigger y first. It's just, to me, I can do it better. 27,800 minus 23,400 over 2012. I got to come back to here. 2012 minus 2008. And I'm kind of lazy to do the math, to be honest with you. 0, 0. Gotta make sure I wrote down the right numbers. 27,800. So all I really care about, I'll let you do the math. Make sure we know those are zeros here. Zero, zero. Okay, so 27 minus 23 is 4. 8 minus 4 is 4. 0, 0, 0, 0, 0, 0. Oh, stop writing. 0, 0. Okay. Over 2012 minus 2008 is 4. That turns into a 1, 1, 0, 0, 0. That's my slope. It's population, though. So that stood for, let's look at the wording of the problem. I guess that's the population in 4 years. So people. Per year. Per 1 year. Because what is it? Let me fix that up. Per year. Because once I canceled out, I'll show you the math in case you're confused. You could have used a calculator, got the same answer, but 4 cancels out to 1, and that 4 cancels out to a 1. I have 1, 1. So really you're only left with 1, 1, 0, 0 people per year. Okay? Let's see what the boss says. There it is. Same answer. Okay. Now what? Another try it problem here. Okay. Population of a small town increased from 1422 to 1868 between 2 other years. They were 2009 and 2012. I'm going to let you work on that. Okay? Same thing we just did. New topic. Point slope form. Point slope form. We just got done doing y equals mx plus b. That was slope intercept form. Now we're doing point slope, which means I need to have at least one point on the line. Any point will do. And I need to have the slope of that line. I need both of those. So that's the gist. I need a point and I need the slope. And all said and done, your equation is right here for point slope. That's how you know it's point slope. Because if you look carefully, here is the y value for a point. Here is the x value for the point. Here is your slope. So your point is x1 comma y1. That writes big because I didn't make it smaller. Doesn't do it there. Let me just erase it. Okay. I'm going to leave it like that so I have a point. x1 comma y1. Once you know that point and you know the slope, you have a y minus whatever this is, y1. Equals to this slope right here m times x, that's built in, x minus the x1 going here, parentheses. So you can see that the y and the x are built in. The x1 and y1 comes from your point, and then the slope is embedded in there. So looking at the textbook notes, they decided to prove to you why this is the formula. I just showed you how to use it. And the theory is always good. If you just start out with the slope of a line, that's what they did, and then multiplied both sides by this denominator, which is x minus x1. So you see the m times x minus x1. You see this fraction times x minus x1. And what happens is these two cancel out, leaving the slope times x minus x1 equals to your y minus y1. See what's left? The whole thing they're trying to do is to rearrange it. So now I already have my y minus y1 equals to my slope times x minus. It's in reversed. The same thing, just in reverse, rearranged. That's what they said. Then if you read the rest of this problem here, it says here, starting here, keep in mind that the slope-intercept form and the point-slope form can be used to describe the same function. It's just two ways of writing it. We can move from one form to another using basic algebra. For example, suppose we are given an equation in point-slope form, which is y minus 4 equals to a negative half times x minus 6. Well, that tells you up front that the ordered pair is embedded in there because the y, this y, and this x are built in. So think about y minus y1. So my y1 must be a 4. And my minus 6 minus x1, that must be my 6. So you're using 6 comma 4. But what they did, they just took that equation. There's your 6 comma 4, and there's your slope of a negative half. They just solved it for y. All they did, which is simply just moving the minus 4 to the other side, plus 4. So when you go plus 4, cancels. Y is the same slope, negative half x, plus 7. So see, it's easy to switch back. Time for you. Let's see. Was this one for you, or is this just I don't know. It's a repeat. Okay, I got to the next problem, but I realized that I didn't give you the problem. I gave the solution page instead. So let's dive into it and just work it out and see what's happening here. So I have to find an equation for this, and I can use point slope form, or I can do slope intercept. Point slope form probably is the easiest because all you need is the slope and one point. Since I have 2 points, I'll use both of those points to find the slope. So my slope will be the difference of my y values. I'll start with the 7 first. 7 minus the 1 over, go to the x's. So I'm doing the x's right here. 8 minus the 5. That gives me 6 over 3, which is a 2. So there's my slope, okay? Now, it doesn't matter which point you pick. It really doesn't. And I'm just going to pick eeny, meeny, miny, mo, catch a tiger by the tail. I'll go 5, 1. Doesn't matter which one I pick. Remember what the equation is. Y minus y1. That would be this right here. Y minus 1 has to be the slope, which we found out to be the 2, times x minus, I got to go here and get my x1 right here, 5. So there is a perfectly good equation. Now, it may not match what they had. Let's see what they had. Y minus 1 equals 2x minus 5. They read my mind, I guess. It would have worked the other way too, except you wouldn't notice it till you solved it for y. So there is a legitimate equation, but a lot of people like to solve it for y because that's hard to put in a calculator. It's hard to put that form in. So if I was to go further, I would move the 1 over, the minus 1. And so it's out here. But remember, to break this apart, I'd have to distribute the 2. So my y will be equal to the 2 times x, which is 2x. 2 times the negative 5 is a negative 10. But don't forget, I brought over a 1. So y equals 2x minus 10 plus 1 would be a minus 9. Does that agree with the solution over here? Looks that way. So you have two equations. We actually killed 2 birds with 1 stone because we have the first equation, which is a perfectly good equation. It's just, not that one. It would have been this one right here. Sorry, this one right here. Perfectly good equation in red. And then we create another equation. They're the same equation. One is easier for a calculator than the other. All right, let's talk about interpreting an equation from a linear function. We already have a graph, and I missed the first part up here. Let's see, there's a try it number. Again, it's 2 points. Find the equation, the line, and it says, then write it in slope intercept. So they're making it us do, whenever you have 2 points, it's always better to do the point slope form first. So I'll call that PS, point slope, meaning y minus y1 equals the slope times x minus x1. So I got to find the slope. So I'll do this. I'll do the work for the slope up here. And I'm going to go with, I always take the y, that's the biggest y. I always do that. So that's a 3. And I'll subtract a 0. So 3 minus the 0 over the negative 1 minus the 0. Well, that's not very exciting. That gives me the slope is just 3 over a negative 1. And I'm going to write that as a negative 3. So there's my slope, negative 3. Either way, I need it because it's going to go right here. And eeny, miny, mo, pick a point. Pick a point. I'm going to pick the easiest point I see. I'm so lazy. I'm going to pick 0, 0. So watch this. Y minus the 0 equals the negative 3 times x minus the 0. What does that turn into? Y equals to 3x. Okay, so do I have 2 equations? Yes, I do. This is my point slope right here, but then it turned into a slope intercept. Unfortunately, the intercept is at 0, 0, because next to the 3x would be a plus 0. So the slope intercept is 0. All right, next thing, writing and interpreting an equation for a linear equation. So let's see what damage you want us to do. Now that we have written equations for linear functions in both the slope-intercept form and the point-slope form, we can choose which method to use based on the information we are given. That information may be provided in a graph, a point, and a slope, or 2 points, and so on. So what'd they give us? They gave, this one is kind of cool. Maybe I'll play devil's advocate, because I notice here that they gave me the B. There's the B. And all I need Now, to go with that b is the slope. And so if I take this ordered pair that they already gave me and just make my little triangle here, I can easily calculate my rise over run. Just be careful. The rise is this distance here. 1, 2, 3. That's considered a positive 3. But the run, pay attention here, starting from here, that's a 1, going that left, 2, 3, 4. Okay, so that's a negative 4. Why is it important? Because the slope obviously is decreasing. That line is decreasing, so it has to have a negative slope. So since I went up here and went left this way, that's why you get a negative in there. So I know my slope is going to be a negative rise 3 over 4, 3/4. So now that I know B was the 7 right here, if B is 7 and the slope is negative 3/4, then look at this, y equals to a negative 3/4 x plus 7. There's my slope intercept form. Now, let's go ahead and do it with the point slope. This is slope, intercept. Now I'm going to do point slope. Well, I had to find the slope for either of them anyway, so I didn't waste any time. Y minus y1 equals slope times x minus x1. Remember what stays permanent. This y is built in. This x is built in. The slope comes from here. So, and I got to pick a point. Any point will do. I'll pick the 0, 7. Why not? Same point. I will pick, the slope is negative 3/4. I'm going to use the 0, 7 point. And let's see what happens. Y minus my y1. That happens to be the y that I'm using, 7. Has to be my slope, which was a negative 3/4, times x minus, well, that's a 0. So that doesn't help. Y minus 7 is a negative 3/4 x. Technically, I could have stopped right here and said, well, that's my point slope. Because it truly is. It's just, who writes it x minus 0 and leaves it? Nobody. But look what happens. Just, a coincidence. Move the 7 over. Y equals to negative 3/4 x plus 7. Does that answer look familiar? It's the same answer. Turning it back into a slope intercept. So it's all related. It's all related, Okay. Please tell me I didn't do another solution. No, these are notes. These are just something. Same problem we just did. That's what it is. It's the same problem I just did. Let's see. Look what they did. Negative 3/4 slope. Yay, I'm right. Look what they did for point slope. Looks a little different. They use the other point, 4, 4. If I go back up to that line, does it have 4, 4? Yeah, I didn't use that point. Uh-oh, I didn't use it. Well, let's see what happened. Y minus, I'm using 4, 4 now, okay? 4, 4. That's my x1 and my y1. Okay, that's what I'm going to use. Y minus y1 is a 4 equals my negative 3/4 times x minus a 4. Well, that's fine. That's my point slope form, but it didn't match mine on the other side. That doesn't mean it's wrong. Okay? That just happens to be an answer. But now look what happens if we solve this for y to turn it back into, since this 4, 4 was not the y-intercept. So I can't just create slope-intercept form. I'm going to have to take this bad boy and solve it for y and see what happens. So I look down here. Uh, it looks like the author distributed this first. That's fine. Negative 3/4 x. Negative times negative is a positive. 3/4 times 4 turns into a 3 because, oops, I don't know why it erased on me. 3/4 times 4 cancels the 4s, gives you the 3. So I got a plus 3. Negative times negative is a positive 12/4, which is 3. Bring the 4 over, add 4, and look at this answer. Does that look familiar? Negative 3/4 x plus 7? I think it does. So this is the same as using the other point. This looks different, but it really is the same. It's just in a different form. Okay. They're just talking about the two equations correspond to each other. Wonderful. These are your steps: how to, given a graph linear function, how to write the equation to represent the function. Identify 2 points is always the best thing to do. Use the 2 points to find the slope. You could also determine where the line crosses the y-axis if it's possible to see it. Sometimes it's not. So that is probably maybe you can. But either way, you can either substitute into the slope and the y-intercept if you can find this, if you can find it, or use a point slope format. So make a decision what you have. Another one, got a picture. Now, I'm looking at this problem and this graph. How would I find a couple points? I'll just zoom in a little bit and see. I don't see anything. Let me change the color so you can see me looking up that line here. I don't see any good point here yet. I don't see any good point. I don't see any good point. Maybe right here. That's a good point up here. And was there another one that I missed it? Oh, yeah, probably I did miss the one down here. I could use those two. Maybe I could use this one up here too. So there are points there. So you decide what would you use. If you're confident at 0, 2, why wouldn't you just use that as my y-intercept? That b is a 2. And then the slope, I'm going to do my cheater's method again. By the way, the slope is in a positive slope direction. So 1, 2, let me see it. 1, 2, 3. 1, 2. Oh, I'm sorry, these are counting by 2s. So I didn't label that. It is 0, 2, but it counted up 2, 4, 6. 2. So my slope was up 6, to the right 2. That's a 3, slope of 3. So if I choose, I already have my slope and y-intercept. Y equals 2, 3x plus the 2. So there's one equation. But what if I didn't notice that I had this point right here? What if I only saw negative 2, negative 4 over here, and I saw 2, 8? What if those are what I saw? Well, then I'll probably have to find the slope between those 2 points. And if you think about it, if I go from here to here, I should get the same slope. Let's see if I get a 3. Remember, this counting by 2s. 2, 4, 6, 8, 10, 12. So that slope is 12 over 2, 4. 12 over 4. Hey, same slope. Or you could have just said slope is negative 4 minus 8 over negative 2 minus 2. That turns into negative 12 over negative 4. It's also a 3. So we get the same slope 3 different times, which is good news. You can't make mistakes. So anyway, back to using the slope intercept. Y minus y1 is the slope times x minus x1. Pick a point. I'm going to pick the point that doesn't have any negatives, because when you have negatives, they cause problems. We make mistakes because we're only human. Y minus 8 equals, I'm convinced my slope is 3, so I found it 3 times, equals x minus the 2. And guess what? I'm going to keep that. If I solve that for y, I should get the exact same answer as that. Yep. 3x plus 2. But I feel confident that the point slope... Oh, I got the solution here. Let's see. How does it look? Let's find out if we're right. Slope was 3. Okay, that's good news. And y plus 4, x plus 2, that may or may not be the same one. Did they use the same point that I used? No. But I did get y equals 3x plus 2 as the y-intercept, so I think that was my answer. I can go back and look. Will represent the same equation. You grab 2 different points, it just looks different, but if you solve it for y, it's the same answer. Okay. It's another example. Write an equation for a linear function given 2 points. Well, we just did that, guys. I'm not going to finish it up for you. I'll start it out. My 2 points are 3, negative 2. That's an x. Negative 2. Other point, 8, 1. Remember, f of something means y. It's not writing good that way. F of something means y. That didn't really help either. But I said it. So, what do they want? What kind of form? I don't think they said. Oh, yes, they did. In slope intercept form. Well, great. Oh, here's the bad news. I don't know what the y-intercept is. I would not do this in slope intercept form. But because they said to, let me show you how you do it. You ready for fun? We need the slope. Either way, we need the slope. I don't like that right like that. Slope is, I'll start with the 1. Oh, well, the other y is negative. It's okay. 1 minus negative 2 over 8 minus 3. 8 minus 3. You just have to be careful because I put a minus here, right? That becomes a plus. 1 plus 2 over 5. 3/5. So I have my slope, but I don't have the y-intercept. I could graph it and see if it comes up, but I don't want to take that time, and most likely it isn't going to be I don't know. I'd have to, can't read the author's mind. So here's what I do. Take your y equals mx plus b. B is what I don't know, but I know the slope, and I know a y, I know an x, as long as I pick a point. So what point would you pick? I'd pick 8, 1, to be honest with you, because there's no negatives. So my 8 has to be my x, and my 1 has to be y. My x has to be 8, and my y has to be a 1. Plug it in. 1 equals to my slope of 3/5. I hope that's 3/5. And my x is an 8 times 8 plus b. This isn't looking very pretty. I'm just going to take a fast look before I get too involved. 3, -2, and 8, comma 1. 1 minus minus 2 is a 3. 8 minus 3 is a 5. Yeah, I think I'm agreeing with that slope. And then I picked the 8, comma 1. So I went, y was a 1 equals the 3/5 times the 8. Oh, it's ugly. 1 equals to, put a 1 under there, 24/5 plus b. So what do I do to solve for b? I know you love fractions. I got to move the 24/5 over. And what does that turn into? It looks more like this. 25/5. Let's see, 25 over 25. No, why am I using 25? That's a silly number to use. A 1's the same thing as 5/5. 5/5 minus 24/5 is a negative 19. That's a 5 there. 5 equals to b. Not sure if I'm 100% right, but I'm going to check it here. But here's the equation then. Y equals to 3/5 x. What did I call that? Minus 19/5. Ugly, ugly, ugly. That's what they wanted, if that's what they want. Assuming I'm right, though. Let's see. Check it out. Remember what their slope is? What I think it is? What my y-intercept I think it is? Let's see. Looking over here. There's my 3/5. And if I can look down to the bottom, y equals 3/5 x minus 8. Wow. I think I'm going to go get me a potato chip because I'm proud of myself. Here's a try it problem. That's probably for you. Okay? If you need help, I'll be happy to look at your work. If you aren't in my class, you can send me a message. Modeling real-world problems with linear functions. Well, why would I do that? Well, because a lot of things are linear. So it doesn't really matter what the things are. You're just going to still find a slope, and you're still going to find 2 points. And you can find the initial value, that is that y-intercept. That would be nice. That's my b. If you can find that, that's great. And then find your slope. Okay? So that's just notes. Okay, example 10. Using a linear function to determine the number of songs in a music collection. Marcus currently has 200 songs in his music collection. Every month he adds 15 new songs. Well, first of all, that's not a lot of songs to begin with. And then 15 songs a month, people rip music or pay for music all the time. So write a formula for the number of songs. Formula means equation, called n. And in his collection, as a function of time, and what does time stand for? Number of months. How many songs we have in a year? There's 2 ways of looking at it. You know, if you start out with 200 songs, this is month 0. 200 is month 0. Think about it. I start there. In 1 month later, I'm adding 15, so it's 215. In 2 months later, I'll add another 15. That's 230. In the 3rd month, you got the point, 245. And I could keep going and keep going till I get to 12. You could do that. It's linear. you're adding the same number of songs every time. The slope is constant every month. That's 15 songs per 1 month. Your slope is very constant. But let's look at it like this. Number of songs in the collection with a variable of t for time, which stands for how many months that are passing. He starts out with 200. So at time t is 0, and look at right here, I've already labeled it right here. At time t is 0, he has 200 songs. So that's your y-intercept. And there's no rule that I can't put my y-intercept in front. Plus, every month I have 15 songs times t. Remember what t stood for, number of months. So there's my equation. So I continue the process and say, well, after a year, t must be 12. So this doesn't count. This one doesn't count. This one is the original. 0, month 0. So I need 12 months after that. So n of 12 has to be 200 plus 15 times 12. So 15 times 12 is the same as 15 times 10 plus 15 times 2. 15 times 10 is 150. 15 times 2 is 30. So you can use a calculator. 200 plus 180. So I think after a year he's up to 380, label it, songs. And I think, is that the solution over here? Yeah, I got the solution over there. And I think I'm right. Okay. All right, using a table or tabular form to write an equation of a linear population. So here, let's see what's happening. My number of weeks, W, would be the same thing as X. My population as a function of W would be the same thing as my Y. Pleasant story. What's happening here? From 0 to 2 months, that's 2 months, I increased 80 rats. And so look at here, from 2 to 4, I increased another 80. Just take a look at it. 1080 plus 80 gives me 160. 1160. 1160 plus 80 gives me 1240. So I know every 2 months I am going up by 80 rats. That means per month, I'm sorry, not month, per week. These are weeks. Per week is 40 rats. Okay? So my slope has to be 40 because every week I'm going up 40. Every 2 weeks I'm going up 80. That has to be my slope. And I'd be silly not to use 0, 1000 because that, if you have 0, 1000, think about it, 0, 1000, that's your y-intercept. When the x is 0, then this becomes the b. So here's my equation, very simple. Y equals, I can't use y, let's follow the directions. P, population of rats, per week, that's why I had to take those 2 weeks and divide it by 2 to get to 40 instead of 80, has to be I started out with 1000, and my slope is 40 per week. That's W. There's my equation. Let's find out what I'm going to have in, do they want to know in a year? What did it say? Oh, they just wanted the equation. No, they don't want me to use it for nothing. That's fine. Then I think I'm done. Let's check out the boss and see. And let me delete it. Oh. Is this the same problem? Hmm. Let's see, 40. Yeah, I see it here. 40 W plus 1,000. And they did a calculation of slope using 2 points. I cheated. I just knew that it was linear. I guess I should have done what they did, but I used a little bit of common sense. And there's just another one. There's a try it for you, okay? So try it for you. This one is counting by twos again, so depending on what we're doing here, a new plant food was introduced to young trees to test the effect of the height of the tree. So the trees are growing, and so we're going to, they're testing young trees. Shown is the height. So x's and heights, that stands for my y's. When we first measured the tree, or trees, or whatever, it was 12.5. Unit would have been in, does it say? In feet. It does say it right here. Okay, so it's 12.5 feet, and then in 2 months, it's 13.5. So I'll do this. Not by just saying, "Oh, I already have the y-intercept," and I guessed my slope. I could still guess my slope, but it's going to be a little harder to figure it out. Not really. I already have it in my head, but let's just do it right. Let's find the slope. And the slope has to come from 2 points. So I got to pick 2 points. It doesn't matter which two. Let me make it simple. Let me take the 12, 18.5. And let me take the other point. Let me take the 2 here. Let me take that one. 2, 13.5. I'm making it hard for myself. So the slope is going to be, I'm going to take this 18.5, subtract the 13.5, divide it by, and I got to come back up. But since I did the 18.5, I got to go pick the 12. 12 minus the 2. That slope is, I wish somebody was here to give me a calculator. I think it's 5 on top. 5 over 10, which is 1/2, which was the answer I had in my head that the slope was going to be, because I did this. 12.5 to 13.5 is a total of 1. So cut that in half to get the 1 here. So that would have been really a half. So you'd be going up to 13. 12.5, so that'd be a 13. So I knew it. Either way, there's my slope. And I would be silly not to use point slope form. I'd be silly not to use this. So y mine equals to the slope 1/2. Am I using the wrong variable? I am. It should be h of t. Let me erase it to cover up the evidence. H of t is, well, I started out with 12.5. That's how high I am. 12.5 minus, my slope is plus, I'm sorry, 1/2, and we're doing the variable of t for time. Is that correct? No, x. X. So that would be my equation. Why can I use 12.5? Because mx plus b, if I wrote mx plus b, 1 half x plus the b, 12.5. Same answer. Okay, so let me... that one will not be solved for you in the book because it's a try it problem. I think that's the answer. All right, so I finished it up. And I did something different for you. I put all the pages, copied the problems even in here. But it's better to go to the book. But for those that don't do that, you should be doing from pages 178 to about 185 multiples of 3. Stop on number 54. So you're only doing 20. 3 goes into 5 once, 2 left over, 20. You're only doing 18 problems. And I have them all in here if it works for you. You can always pause it on here. And this might be the last page. So, with that being said, I'm out of here.